Welcome to CHEM. Now today's video is on acids and bases part 7 video, and here we are going to deal with Lewis theory for acids and bases. Now before starting, already 6 videos are uploaded in channel, you can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to CHEM, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. Now what does Lewis theory state? It states that acids are those substances which can accept electron density, whereas bases are those substances which can donate electron density, and this is very important to understand. Now if you try to take examples, then in this case for acids, any cations have the ability to accept electrons. So we can write M with a power of N plus. So all cations are acids. Again, if we take BX3, that is boron halide complexes, then those are also Lewis acids. AlCl3 whole 2, that is also Lewis acid. SnCl2, then SbF5, these have vacant Ds, so these are also our acids, Lewis acids. Now if we go for Lewis bases, then all anions are Lewis bases. Similarly, ammonia has electron density in it and it can donate its electron density, so it is also Lewis base. RNH2, R2NH, PPH3, all these have the ability to donate their lone pairs and thus can be told as Lewis bases. Now, using this concept, we can answer that CO2 behaves as Lewis acid in presence of OH minus. Another question whose answer we can get from Lewis theory is that SO3 is Lewis acid or Lewis base. What is SO3? Whether acid or base. Next question is SiCl4 cannot behave as Lewis acid towards Cl minus, but SiF4 can act as Lewis acid towards F minus. Similarly, last question is iodine and bromine can behave as weak or mild Lewis acids in presence of donor solvents like water, acetone, etc. Now these questions will be answered. Now you have to understand that in this case neutralization can occur by transfer of electron density from Lewis base to Lewis acid, and using Lewis base and Lewis acid we can get a Lewis adduct. For example, if we take one benzene ring and to it we join a chromium which is acting here as Lewis acid, and the other part is also joined with a benzene, then we can consider this part as our Lewis base, this part as our Lewis acid, and this part as our Lewis base, as benzene will donate electrons from both sides and chromium will accept that electron, and this particular form is known as Lewis adduct. Now we will see few more examples. Suppose if we consider a compound containing amine, that is N with 3R, that is 3-degree amine. Here it has lone pair, so we can write it as Lewis base. It can react with a boron compound which has 3 fluorine attached to it, BF3, which acts as Lewis acid. So in this case this lone pair gets donated to boron. Now this reaction on further proceeding we obtain this kind of adduct, Lewis base and Lewis acid adduct. So this is one of the examples, right? Now we will see the next example. This is also presence of C5H5 minus, which is acting as a Lewis base and donates its negative electron charge density. So if you see here, its formation can be done if we take C5H6, then it has 2 protons. On adding any kind of base, this base will try to abstract one of the protons and this electron density will be remaining here. So ultimately what we get is this C5H5 minus, and this is a Lewis base. Now another example we have already seen, that is this one, adduct formation. So this adduct formation can also occur like this if we take a 5-membered ring like this and iron is taken in between and another ring which is like this. This can also be formed where this acts as Lewis base, this acts as Lewis acid and this acts as Lewis base. This is also a Lewis adduct and this particular compound is known as ferrocene. Now we are going to answer the question, that is why CO2 behaves as Lewis acid in presence of OH minus. So if you draw first CO2, then it looks like this, C double bond O, and if OH minus is added, in this case this acts as Lewis acid and this acts as Lewis base, and this particular OH minus attacks carbon present here and one of the double bonds get open, and what we get ultimately is like this, C double bond O, O minus OH. So in CO2 the carbon center is acting as electron deficient center due to presence of 2 electronegative atoms which we can see here, which is oxygen in either of the sides. And if we try to draw the molecular energy diagram of CO2, then the LUMO, that is lowest unoccupied molecular orbital, is of carbon character and it is also low lying. Hence, it will be able to accept the electron density from this O readily at the carbon center, and this accounts for the Lewis acidic behavior. What is HOMO? What is LUMO? You can learn. I will give the link of that video in the description box as well as the I button above this video. Now, the next question is that whether SO3 is Lewis acid or Lewis base. This needs to be get answered. Now, you have to understand that this SO3 can act as both Lewis acid and Lewis base. How does it occur? If example is required, then see this one. There is SO3. Now, if we take H2SO4, what is the structure of H2SO4? 2 double bonded oxygen and 2 OH. This is the structure. Now, if we try to undergo the reaction, then this one of this lone pairs will attack this proton, okay, and this bond will go here. Another bond from here will attack the sulfur. So if you can observe here, what happens is that this particular H2SO4 here is donating electron as well as accepting electron. Similarly, SO3 here is donating electron as well as accepting electron. So as a result, both of this is acting as Lewis acid plus Lewis base in SO3 as well as for this one, that is H2SO4. And what we ultimately get is oleum, which looks like this, S double bond O, double bond O, OH, oxygen, S double bond O, double bond O and OH. And this compound is known as oleum, and we can write it as Lewis adduct. This is also a kind of Lewis adduct. Now we will answer the next question, that is SiCl4 cannot behave as Lewis acid towards Cl minus, but SiF4 can act as Lewis acid towards F minus. So if we try to draw the reaction, which is most important in this case, so SiF4 looks like this, and we have seen in the question that it says that it acts as Lewis acid, and we have 2F minus which is acting as Lewis base, right? So this F minus will try to attack the silicon center. So what we get ultimately is SiF6 2 minus. But in case of SiCl4, if we add 2Cl minus, the reaction does not occur and it does not behave as Lewis acid, because if you see, this acceptance occurs as silicon has vacant 3D. Okay, that will help it to accept the electron density in the corresponding tetrahalides. But this only occurs in case of SiF4, whereas SiCl4 do not show such case, because formation of octahedral Lewis adduct is sterically favored in case of F minus, as the F minus has 6F which is smaller in size in compared to 6Cl. As a result, it is not possible when chloride is treated with SiCl4, since the formation will cause steric hindrance and it will be sterically disfavored. That's why it does not show Lewis acidity in this case. And this question is very important. Now we will see the last question, that is iodine and bromine can behave as weak or mild Lewis acid in presence of donor solvents like water, acetone, etc. Now you have to understand that upon addition of iodine, bromine to a donor solvent like water, acetone, there is a formation of 1:1 charge transfer complex. How it is formed? Let us see. If you draw iodine, here is iodine, and we have a acetone like structure. Okay, we are considering here acetone as the donor solvent. So it has 2 lone pairs of oxygen, right? Another iodine is present here. Again, here also there is oxygen with 2 lone pairs, here one, and the other structure. Similarly, here also another iodine, and this structure continues with the lone pairs, right? So there is a transfer of charge in between and formation of a 1:1 charge transfer complex. Here also these bonding goes on for each cases. So this is the 1:1 charge transfer complex, and here in this case electron density from the lone pair of donor solvent which we see here are donated to the vacant sigma star, that is LUMO of iodine. Since iodine is accepting electron density, so it will behave as Lewis acid, and it is due to this formation of 1:1 charge transfer complex that the color of iodine appears to be brown in presence of donor solvents. So iodine color appears to be brown in presence of this donor solvent. Color changes due to the formation of this charge transfer complex. So this much for today. Hope this was helpful. Do not forget to like, share, subscribe and comment. And in the next video, we are going to deal with hard and soft acid base theory.